Hi, welcome to video lecture on geometry of linear transformations in R2. So this is just the first sort of subsection of section 6.5 in our textbook. We're not going to be covering the rest of that section. So these are basically applications of linear transformations in the plane. And these applications are of interest, for example, to people who do computer imaging. So computer scientists, designers, use linear algebra all the time. And in particular, if you're going to transform images, two-dimensional images, you're going to need to use 2x2 matrices. You have to figure out how to represent the transformation with a 2x2 matrix. So we're going to look at sort of building blocks for those types of linear transformations, the matrices that we'll need to use. So the building blocks are the sort of basic linear transformations that we'll use to get other linear transformations. So the first basic type is a reflection across a line, and there are three basic lines: the x-axis, the y-axis, and the line y equals x. And then the second type, basic type, is called an expansion or a contraction. And there are two different ways that you can expand or contract. You can expand or contract horizontally, or you can do it vertically. So there's basically four types, basic types of expansions. And then the last type is called a shear, which is a little tricky, but we'll look at how to get the matrix for a shear, and we'll look at how it's different from an expansion. So, although sometimes it looks like an expansion, it is not. It's very different. So these three types are basic because each of these types is represented by an elementary 2x2 matrix. And you have to remember what an elementary matrix is. Remember that an elementary matrix is a matrix that you get from the identity matrix using a single elementary row operation. Okay, not more than one at a time. So let's just start looking at the reflections. So the first reflection we're going to look at is something we've already worked with before. It's the reflection across the line y equals x. And we saw that when we take a vector v1, v2, the two components, and we reflect it across that line, we get the new vector, which is just the two components are swapped. So the t of v1, v2 is just v2, v1. And remember, to get the standard matrix for any linear transformation, what we have to do is we have to compute the images of the two standard basis vectors. So t of 1, 0 is just 0, 1. You just swap the components. T of 0, 1 is just 1, 0. And then we can write down the standard matrix using those two vectors as the columns. So the standard matrix for this linear transformation has columns 0, 1, 1, 0, the images of the two standard basis vectors. Now this is an elementary matrix because we can tell by looking at it that all we had to do to the identity matrix is swap the rows. So it's a single row swap on the identity matrix. All right, so the other two reflections are reflections across the axes. So let's look at a reflection across the horizontal axis. So if we start with a vector v, whose components are v1, v2, and we reflect that across the x-axis, what have we done to it? Well, the horizontal component remains the same. v1 is just going to be v1. The first component is just going to be v1. But the second component is going to be the opposite of the original second component. So t of v1, v2 is just going to be v1 negative v2, or the opposite of v2. So let's get the standard matrix for this linear transformation. We do that by performing the transformation on the two standard basis vectors. So let's look at what happens to the first standard basis vector, 1, 0. So that is the vector E1, which is just sitting on the x-axis. So when you reflect a vector that's lying on the line, when you reflect it across the line that it's sitting on, it doesn't actually move. So T of E1 is just E1. So that's the first image. T of 1, 0 is just 1, 0. The other standard basis vector, E2, is sitting on the y-axis, and when we reflect it across the x-axis, we do get a different vector. It has the same horizontal component, 0, but the vertical component is now the opposite of the original vertical component. So T of 0, 1 is just going to be 0, negative 1. All right, so now we have our two columns for the standard matrix. The columns are 1, 0, 0, negative 1. And once again, we can see that this is an elementary matrix. This is a matrix that we get by a single row operation on the identity matrix. And that row operation is just multiplying the second row by the scalar negative 1. So that's the elementary row operation that was performed on the identity matrix. All right, so let's look at the last reflection, which is across the y-axis or vertical axis. So let's start with a vector v, whose components are v1, v2. Reflecting that across the y-axis, what do we get? Well, the second component stays the same, and the first component just goes to the opposite, okay, or negative v1. So T of v1, v2 becomes negative v1, v2. So getting the standard matrix requires finding the images of the two standard basis vectors, T of 1, 0 and T of 0, 1. So if we look at 1, 0, that's sitting on the x-axis, and we reflect that across the y-axis, and we do change only the first component. So it goes to negative 1, 0. If we look at the second standard basis vector, E2, its components are 0, 1, and we reflect that across the vertical axis. Well, it's sitting on the vertical axis, so it's not going to change at all. So T of E2 is just E2. So T of 0, 1 is 0, 1. So notice that we have a couple of transformations that changed one of the standard basis vectors but didn't change the other one. And that's an interesting factor. We're going to look at transformations that have what are called fixed points. So in this last linear transformation, the vector E2 was a fixed point of the linear transformation. And there might be other fixed points, but we'll look at that in a few minutes. So let's get the standard matrix for this linear transformation. We just take those two image vectors and line them up as columns. So we get negative 1, 0, 0, 1. And once again, we see that is an elementary matrix. All we did to the identity matrix is multiply the first row by negative 1. So we can see that all three of these reflections that we just looked at are elementary matrices. All right, so let's look at our first example on the worksheet. Example 1, we're starting with a linear transformation T that just reflects everything across the line y equals negative x. So this is not one of the basic ones that we just looked at. And then the question is, find the image of the vector 2, 3. So what we're going to do is we're going to try to first visualize what's going on, and then let's get the the standard matrix for this transformation and use it. So first of all, there's the line y equals negative x. It goes through the origin, has slope -1. If we take one of the standard basis vectors, so let's take E1. E1 is sitting on the horizontal axis, and we're going to reflect it across this line y equals negative x. So it goes down and ends up landing on the vertical axis, but it's going in the negative direction. So t of E1 is 0, -1. And let's look at E2, where that goes. If we reflect that across, so it's sitting on the y-axis right now. We reflect it across this line, and it lands on the x-axis, but it has a negative first component. So t of E2 is -1, 0. So let's put this together and look at the matrix. So t of E1 is 0, -1. T of E2 is -1, 0. And lining those up as the columns, we get this matrix, 0, -1, -1, 0. So is that an elementary matrix? Well, the answer is no. We couldn't get this matrix from a single elementary row operation on the identity matrix. We can see that there are actually 3 separate row operations here. There's a row swap, and one of the rows has to be multiplied by -1, and then the other row has to be multiplied by -1. So this is a combination of 3 elementary row operations. It's not an elementary matrix. All right, so now that we have that, it's not elementary. What are we going to do with it? We're going to find the image of 2, 3. So let's just multiply by the matrix. And what we get is -3, -2. So we've actually swapped the 2 components and multiplied each component by -1. So that's actually 3 separate elementary transformations. All right. So let's look at a new definition. So a vector V is called a fixed point of a linear transformation T when T of V is actually just V. So a fixed point is a vector that doesn't get changed by the linear transformation. So let's do a quick example of that. Let's look at the linear transformation in example 1 and find its fixed points. So find the fixed points of the linear transformation in the last example. So T of V1, V2 is equal to V1, V2 when the product of the standard matrix times V1, V2 is equal to V1, V2. So this is the definition of being a fixed point. So let's see, what does the product give us? So it gives us 2 equations. -V2 is equal to V1, if we do the actual product, and -V1 is equal to V2. So basically it's saying that the 2 components just have to be opposites. So that's a lot of fixed points. So let's describe it. The set of all fixed points of the transformation is the set of ordered pairs -t, t, such that t is any real number. So it's all the ordered pairs such that the 2 components are just opposites of each other, -t, t. All right, so that's a lot of fixed points. It's not just the 0 vector, right? The 0 vector goes to the 0 vector, but it's all the vectors that actually lie on the line y equals negative x. So that's what all the fixed points are. Okay, so let's look at the next type. So we're going to look at expansions and contractions, but I told you there were two types. There's the horizontal ones and the vertical ones. So the standard matrix for a horizontal expansion or contraction looks like this. The two columns are K0 and 0, 1. And that's because if you expand the first standard basis vector, 1, 0, if you expand that horizontally and not vertically, all you're doing is you're multiplying the first component by a scalar k. Okay? So the second component doesn't change. So 1, 0 goes to K0. And now the vertical expansion is the opposite. So you would not change the first standard basis vector, 1, 0. If you're expanding it vertically, its vertical component is already 0. So a scalar times 0 is just 0. So the first standard basis vector goes to itself. It's a fixed point. The second basis vector is the one that gets changed. So 0, 1 goes to 0k because the vertical component, the second component, gets multiplied by the scalar k. So it's an expansion if it's a horizontal expansion if the vector is scaled by a constant amount horizontally, or a contraction is scaled by a constant amount just horizontally. The vertical component isn't changed. And then it's a vertical expansion or contraction if the vector is scaled by a constant amount just vertically, and the horizontal component stays the same. So now that the expansions are the transformations where k is greater than 1. And the contractions are the ones where the scalar k is between 0 and 1. So notice k is a positive number, but if k is between 0 and 1, we're actually contracting either the horizontal component or the vertical component. If k is greater than 1, we're expanding either the horizontal component or the vertical component. So let's look at what these look like. So a horizontal expansion, we're going to multiply the vector v1, v2 by the matrix k0, 0, 1. And what we get is k times v1, v2. So we've just multiplied the horizontal, or the first component, by the scalar k, and we've left the second component alone. So that's a horizontal expansion if k is greater than 1. So if this is our vector v, the components are v1, v2, and we multiply just the first component by a scalar greater than 1, we're getting this vector, k times v1, comma v2. So the vertical component stays the same. It's the same height or same distance from the x-axis. But the horizontal component moves horizontally. All right. So let's look at the contractions, horizontal contractions. Take a vector v1, v2, and we're going to multiply it by the standard matrix, and we get k times v1, v2, just like with the expansion. But this time, k is between 0 and 1. So it's actually going to contract horizontally. So it stays the same height, but the horizontal component gets shrunk. So we go to kv1, comma v2, but kv1 is smaller than the original v1. Okay, so let's look at the vertical expansions and contractions. So we start with a vector v1, and let's multiply it by the standard matrix. And the first component stays v1, but the second component changes. It becomes kv2. So that means the vertical component, if k is greater than 1, it got moved up. The second component gets moved up. Vertical component stays the same. So the image of v1, v2 is v1 and then k times v2. And since k is bigger than 1, it's higher. All right, so if it's a contraction, the multiplication is the same. So we get the vector v1, k, v2. But because k is less than 1, we're moving it vertically down. We're contracting only the vertical component. All right. So those are expansions and contractions. Let's look at example 2. Example 2, we have a linear transformation that's defined to be t of the vector xy becomes the vector x over 4y. So part A says, describe this transformation geometrically and represent it graphically for an arbitrary vector in R2. So let's get the standard matrix for this transformation. So t of 1, 0 and t of 0, 1 are going to be our columns. So t of 1, 0 is just 1 over 4, comma, 0. And the other one is just 0 over 4, comma, 1. And so now we can write down the matrix. It's going to be 1/4, 0 and 0, 1 are the two columns. So we can see that k is 1/4. And this looks like it has to be a horizontal contraction. And geometrically, there's an arbitrary vector, xy. We're contracting it horizontally by a factor of 1/4. So that new vector looks like that. That's all we've done. So now let's find all the fixed points of this linear transformation. So remember, we're going to use the definition. We're going to say if v is v1, v2, and it's a fixed point of the linear transformation, then t of v1, v2 has to be v1, v2. And what does that mean? That means that v1 over 4, comma, v2 has to be equal to v1, v2. So clearly, v1 over 4 is equal to v1. So if I get everything on one side, I get 3/4 of v1 is 0. And because we know we have a product of two real numbers on the left, 3/4 times v1, that product is equal to 0 if and only if one of those real numbers, at least one of them, has to be 0 to begin with. Well, the only one that could possibly be 0 is v1. So all the fixed points of this linear transformation are the vectors whose first component is 0. So that means they all lie on the vertical axis. So the set of all fixed points, let's describe it. It's the set 0, comma, t, such that t is a real number. So those are all the vectors that lie on the vertical axis. The first component is 0. All right, what does that look like? There it is. T of 0t is just going to be 0t. Because when you multiply the first component, 0, by 1/4, you just get 0. All right, so let's now look at shears. So the definition is a little complicated. So let's first look at vertical shears. A vertical shear is defined to be a vertical shift. Now remember, a shift is different from a expansion or contraction. So an expansion or contraction is where you multiply a component by a number. So you're scaling something by a factor. But a shift is when you add a number to one of the components. So a vertical shift by an amount proportional to the horizontal component. That's a vertical shear. So you're shifting vertically. However, the amount that you're shifting by, the amount that you're adding or subtracting, is different for each vector. It's proportional to whatever the horizontal component was. So it looks like this. T of V1, V2 turns out to be V1, comma, and now we're going to add something to V2. We're adding something that's proportional to V1. So it's going to be V2 plus some number K times V1. So this is very different from a vertical expansion or contraction. We're adding something, and in fact, we're adding something different to each vector. What we're adding to the vector is just a number times whatever its horizontal component was. And here, K can be any real number. It doesn't have to be positive. It could be negative. Okay. So let's look at what it looks like. So we're starting with a vector V1, V2. And we're going to add something to the second component. So the new vector is V1, comma, V2 plus K times V1. We're adding to V2 an amount proportional to V1. So look at this picture. Did I add, is K positive or negative? Well, it looks like we've moved it down, but V2 was already negative, and V1 was also already negative in this particular picture. So K is actually positive in this picture because V1 was already negative, and so if we multiply V1 by a positive number, that means we're adding a negative number. All right, so let's find its matrix. So let's take the two standard basis vectors in R2. The two vectors are 1, 0, and 0, 1. So T of 1, 0, if we're scaling vertically, if we're shearing vertically or shifting it vertically, the first component doesn't change. So V1 was 1, so the new V1 is just 1. But the second component is going to be V2 plus K times V1. Well, V2 was 0 and V1 was 1, so it's 0 plus K times 1, which is just K. So the first standard basis vector, 1, 0, goes to 1K. The second standard basis vector, 0, 1, what does it go to? So the first component is 0, stays the same. The second component is going to be 1 plus K times 0. So 1 plus 0 is just 1. So the second standard basis vector is a fixed point of a vertical shear. Let's see what that looks like. The matrix looks like. So the matrix A is going to have 1K as the first column and 0, 1 as the second column. So let's, and that is different from a vertical contraction or expansion. So now let's look at the horizontal shear. So horizontal shear is another definition that's slightly complicated. It's very similar. We're going to horizontally shift each vector by an amount proportional to the vertical axis, vertical component. Okay, so a horizontal shift by an amount proportional to the vertical component. So again, each vector gets shifted horizontally, but by a different amount. Depends on whatever its whatever its vertical component was. Let's look at the matrix. Well, let's look at the arbitrary vector, So T of V1, V2. Now, it's a horizontal shift, so the vertical component stays the same. So T of V1, V2, the second component is just going to be V2. But the first component is going to be V1 plus an amount proportional to V2. So the first component is V1 plus K times V2. And visually, what does that look like? We start with a vector V1, V2, and we're shifting horizontally by an amount proportional to whatever the second component was. So the vector goes to V1 plus K times V2, comma, V2. So now let's get the standard matrix for this. So we have to find T of 1, 0 and T of 0, 1. So T of 1, 0, if we're shifting horizontally, we're not changing the vertical component. So the second component stays 0, but the first component is going to be V1 plus K times 0. Well, that's just V1, so that's 1. To get the image of the second standard basis vector, 0, 1, we leave the second component alone. We're shifting horizontally, so the first component is the only thing that's going to change. So the first component is going to be 0 plus an amount proportional to 1. So it's going to be 0 plus K times 1, or just K. So here, the first standard basis vector is a fixed point. And let's get the matrix. So A is going to be 1, 0, K1. This is very different from the matrix of a horizontal expansion or contraction. Okay. All right. Let's look at a quick example. So let the transformation T from R2 to R2, oops, there's no T in there. T goes from R2 to R2, and let it be defined this way. So T of the vector 1, 0 is just going to be 1, 0, so it's a fixed point. And T of 0, 1 is -3, 1. So let's figure out, is this going to be a shear or an expansion? So the matrix for this, we can just write it down because these are the two standard basis vectors. So the matrix for this is 1, 0, -3, 1. So T of some arbitrary vector V1, V2 is just going to be the product of A times V1, V2. And what we get, the first component is going to be V1 minus 3V2. The second component is going to be 0 plus V2. So this is clearly a horizontal shift. So the first component got changed by an amount proportional to the second component. So that tells us that we do have a horizontal shear. Oops. Okay. Let's look at something that people who work in computer imaging are concerned with. The image of some basic object in R2. That basic object is called the unit square. So the unit square is defined to be the area of the region with vertices 0, 0, 1, 0, 1, 1, and 0, 1. So let's see what it looks like. So I plot the 4 vertices. And there it is. That's called the unit square. Each side has length 1. So let's look at a vertical shear of the unit square. So I'm going to shear vertically by an amount proportional to the first component. So I'm going to shear by 3 times the first component. So I'm vertically shifting by an amount proportional to the horizontal component. What does that image look like? The image of the unit square. So all I do is I take T of the 4 vertices. So the 2 vertices that lie on the y-axis, 0, 0, and 0, 1. The first component stays 0, right? But the second component gets shifted by 3 times 0. So basically, the second component doesn't move at all. So the second component stays the same because 3 times 0 is just 0. So those 2 vertices stay put. Right? The T of 0, 0 is just 0, 0. T of 0, 1 is 0, 1. But now the other 2 vertices are going to change because the first component is 1, and so we're going to shift the second component by 3 times 1, or 3. So we're just going to add 3 to the second component. T of 1, 1, for example, is going to be 1, comma, 1 plus 3 times 1. So that's going to go to 1, 4. So that's way up there. And then the other one goes to 1, 3. So here's the image of the unit square under that shear, a vertical shear. Okay? So not all vectors get shifted vertically by the same amount. In fact, for the unit square, the vertices, there are 2 of the vertices didn't get shifted at all, and then the other 2 vertices, that because they had the same first component, their second components did get shifted by the same amount. All right, so let's compare that to a vertical expansion. So let's do the expansion. T of xy goes to x, comma, 3y. So what happens to the unit square under this? Well, we just have to look at the vertices. So T of 0, 0, the first component doesn't change, so that's 0. The second component is going to be 3 times 0, which is also 0. So the first vertex, 0, 0, doesn't change at all. And what about the vertex 0, 1? Well, the first component stays the same, but the second component gets multiplied by 3. So anything that didn't have a 0 in the second component changes. But anything that's lying on the x-axis, it has a 0 in the second component, doesn't change. So 0, 0 goes to 0, 0, 1, 0 goes to 1, 0, but the other two vertices get expanded upward vertically. So 0, 1 goes to 0, 3. 1, 1 goes to 1, 3. And so there's our image of our unit square. So compare the vertical shear with the vertical expansion. These are two very different linear transformations. And now one interesting fact that is not in our textbook, which I think is an important fact and should have been in the textbook, is that shears preserve area, but expansions do not. So you can tell by looking at it that the image under the vertical expansion has area a lot bigger than 1. So the unit square, the original unit square, had area 1 times 1, which was 1. But the image of the unit square under the vertical expansion has area 1 times 3, or 3. So the area of the image under the expansion is 3 times the original area. However, and I'm not going to go through the details, but you can find the area of the image under the shear. The shear, that area of the image will actually be the same. It'll be 1. So shears preserve area and expansions don't. So those two regions have the same area. All right. So let's go to the last example. Example 3 says where it asks us to write the matrix A, which is 2, 0, 2, 1, as a product of two elementary matrices, and then give a geometric description of the linear transformation that it represents. So if we look at the matrix A, we can tell it's not elementary. So what are the elementary row operations we would have to do to the identity matrix to get this matrix? Well, there are a couple of ways to go, but one way is the first step would be to add 2 times row 1 to row 2. So row 2 gets replaced by 2 times row 1 plus row 2. And then after that, the second step would be to replace row 1 with 2 times row 1. So it's 2 separate steps in that order. Okay, you could have 2 other elementary row operations in a different order. But for example here, I couldn't first multiply row 1 by 2 and then follow that by 2 times row 1 added to row 2. It would just be 2 times row 1 and then followed by row 1 plus row 2. It would be two different elementary operations in a different order. But let's follow this path. If I identify these two in this order, I'm going to write down the 2 elementary matrices, E1 and E2. So the first row operation was 2 times row 1 added to row 2. So let's do that to the identity matrix. 2 times row 1 added to row 2 gives us 1, 0, 2, 1. So let's call that E1. And then the second, so that's a vertical shear. Then the second matrix, the second row operation was replacing row 1 with 2 times row 1. So let's do that to the identity matrix. And we just get the matrix 2, 0, 0, 1. Let's call that E2. And we can tell by looking at that that's a horizontal expansion. Okay, so we took a vertical shear and followed it by a horizontal expansion. So that means that A times V, our original matrix A, times the vector V, is going to be first multiply V by E1, the vertical shear, then multiply that by E2, the horizontal expansion. So then A is equal to the product E2 times E1. E2 was 2001 and E1 was 1021. So that means that A represents a vertical shear followed by a horizontal expansion in that order. It's very important. Order is important. So I'll write that down. Order is important. So, for example, if you multiply those two matrices together in the other order, if you do 1021 times 2001, you'll get a different matrix. You won't get A. So make sure you know which elementary row operation has to come before which when you write down these matrices. Okay, so I want to draw your attention to this table on page 336 in section 6.5. This has the basic building blocks for all of these linear transformations. These are the elementary matrices for linear transformations in R2. Remember, we had reflections in the two axes or the line y equals x. Those were represented by elementary matrices. And then we had horizontal and vertical expansions and contractions. And then we had horizontal and vertical shears. Now compare the matrices for the expansions and contractions. Compare those with the horizontal and vertical shears. They're very different. Okay, so you have a WebAssign assignment to do on this section. Make sure you get it done so we'll be ready for Chapter 7. Have a great weekend.